All right, welcome to let's rewind all that. Hello and welcome to CE 3372 Water Systems Design. This is lesson 14. We're continuing with our open channel flow hydraulics review, and today we're going to examine gradually varied flow hydraulics. And so I'm at the blackboard right now and clicking on the lesson 14 link, which should take me to the content server for the class. And as I'm continuing, let me prepare some useful things to add to the screen in the recording. So I want to get the chat box attached, put that down there, and a look at all of our wonderful faces. Interesting, it's actually not. And the participant list. That's mostly so I can keep track of folks coming and going. Not that I'm taking roll per se, but this gives me the ability to tell if something's starting to go wrong with the video. Oh, yeah, something is going wrong. The API stopped working. There we go. And then I want this, pull this over, should go on top of everything. Perfect. Okay, that way I can see a little bit of the chat box, so if you want to type a question there, I'll eventually see it. So very good. Okay, so let's continue with today's lesson description. I believe I got the tool kit repaired, so this link should go to the right place. We'll test that in a little bit. This lesson examines open conduit flow concepts for gradually varied flow. So this is the case where the slope of the hydraulic grade line is not equal to the slope of the energy grade line. And it's actually an important regime of flow for stormwater and wastewater collection systems, because this is where we get the backwater effect and the pooling that occurs in real systems. We have the notes link, which pretty much is replicating the same reading links, but the notes themselves are different. We'll get back to those shortly. The video links, none of those are go to anywhere yet. This lecture has no supplemental data as of right now, and there are some spreadsheets and R scripts, and we will visit those when we get to an appropriate point in the lesson description. As a practical matter, we'll probably use commercial software such as Swim to do these water surface calculations. We'll examine these spreadsheets just to get a quick refamiliarization with what's going on under the hood of that program and similar programs. So let us begin. So today's lesson is a continuation of last time, only now we are adding to the complexity of flow the ability of the hydraulic grade line and the energy grade line to have different slopes. So the principles to keep in mind in gradually varied flow hydraulics are the resistance equations. That's going to be Manning's equation, the concept of specific energy, and the definitions of subcritical, critical, supercritical, and normal flow, which we've already examined. As before, open channels are conduits whose upper boundary of flow is a liquid surface. Storm sewers and sanitary sewers are typically designed to operate as open channels, and the relevant hydraulic principles are the same as last class meeting. This is also an identical slide to the last class meeting. And we'll go back to some nomenclature. In this set, someone's taken the trouble to try to draw it using a drawing package. and the conversion to the new rendering software kind of broke it, but I guess this is good enough. So if you recall, flow depth is the depth of flow at a station measured from the channel bottom. Elevation is the elevation of the channel bottom relative to a reference datum, typically means sea level. In this figure, you'll observe that the dashed line, which represents the true flow depth, and the vertical line for y, which is probably what we would report, are slightly different, and that's related to the slope of the channel. For relatively small slope things, which is most of what we are dealing with in engineered and even natural systems, the difference, the numerical difference imposed by that angular deviation is pretty minor, and it's often neglected. The slope of the channel bottom is called the topographic slope or channel slope, and in this diagram it's shown here as S0 for every 1 unit of run. The slope of the water surface is the slope of the hydraulic grade line, and in this drawing the author wrote the slope of WSE, water surface elevation. There's the rise over 1 unit of run. And they could have just as well written the slope of the hydraulic grade line. Same meaning. And this dashed blue line is supposed to be coincident with where the water flow is, but again, the rendering software kind of broke up the drawing, as is typical of rendering software. The last one is the energy grade line, which in this case is plotted in red, and it's supposed to correspond to the elevation plus flow depth plus energy plus velocity head produces this dashed red line, and its slope is conventionally the friction slope S sub f for 1 unit of run. And here we have the discharge in this piece of channel as velocity, the mean section velocity, times area, the cross-sectional area of flow. So like in closed conduits or in our pressurized systems, the various terms are part of their respective mass, momentum, and energy balances. Unlike closed conduits, the geometry is dependent on the flow value, and the pressure term is dependent on the flow depth. So the pressure term in the Bernoulli's equation for an open channel is replaced by the flow depth. So for instance, y, the depth, is equal to P over rho g at a section. They replace each other in the equation. And so this will go through that nomenclature. The pressure head at the bottom of an open channel at the solid water interface is given by the depth of the water, y. The open channel velocity head is v squared over 2g, so that has the same meaning as it did in pressurized systems. The open channel elevation head is the distance to the bottom of the channel, z. The total head in an open channel, h, is equal to y plus z plus v squared over 2g. The channel slope is given as z1 minus z2 divided by the distance between the two sections. So z1 might be on this left side, and z2 is here on the right side. The difference of those two divided by the distance is the channel slope.
So I was thinking we could play Big Mac. Yeah, so what I want to do is, if we go earlier, I don't know when.
The friction slope is the difference in total head at the two stations divided by the distance between them. So if This location here on the left side of the figure is location 1, and on the right side it's location 2. The friction slope would be the total head at station 1 minus the total head at station 2 divided by the distance between the two stations. So S sub F H1 minus H2 over L. Now uniform flow we've already examined. In uniform flow the water surface is the same as the bottom surface is the same as the energy grade line. And here's the diagram for uniform flow that we've already seen before. In uniform flow, Y1 and Y2 would have the same numerical value. And the slope of the water surface and the slope of the bottom would be the same. And the slope of the water surface and the friction slope would be the same. Now, gradually varied flow removes that restriction and instead admits the possibility that the hydraulic grade line and the energy grade line can have different slopes. But it qualifies that in that the change in flow depth moving up or downstream is comparatively gradual with respect to distance, so not a waterfall. If we examine the energy equation from section 1 to section 2, so the energy is shown as these red bars in this drawing. And these red bars are being measured from the bottom of the channel upward, and I'll explain that representation shortly. If we wrote the total energy at section 1, we would write elevation Z1 plus the pressure head Y1 plus the velocity head V1 squared over 2G. That would be the total energy at station 1. If we repeated that for station 2, we would write Z2, the elevation at station 2, plus Y2, the flow depth at station 2, plus V2 squared over 2G, the velocity head at station 2, plus the head loss. And what this right-hand side of this expression would do for us is it would take us from the datum. We would go Z1 units up, then Z2 units up, then Y2 units up, then V2 squared over 2G units up, then the head loss units up, and we get up to this line. And if we move upstream to station 1 and then start subtracting, we would remove V1 squared over 2G, Y1, Z1, and get back down to the datum. There is a group of terms in both sides of the expression which is represented by the red bars, and that's called the specific energy for a section. And what the specific energy is it's a derived term that's the sum of the flow depth and the velocity head. And combined, they represent the energy at a station that's not associated with the physical elevation of the channel bottom. And specific energy has some utility that we'll see shortly. We can rewrite our energy equation in terms of the specific energy. So the specific energy at section 1 plus Z1 equals the specific energy at section 2 plus Z2. We can perform the indicated algebra and move the Z2 term here to the left-hand side. So we now have specific energy at section 1 plus elevation at section 1 minus elevation at section 2 equals specific energy at section 2 plus the head loss. Well, it turns out that Z1 minus Z2 can be replaced with the bottom slope times delta x, where delta x is the distance between section 1 and section 2. Similarly, the head loss can be replaced with the friction slope multiplied by the distance between the two sections, delta x, as S sub f delta x. And we can make these substitutions and then rewrite the energy equation between the two sections as specific energy at section 1 plus S0 delta X equals the specific energy at section 2 plus S sub F delta X. And that is the first step in a generic equation for gradually varied flow. So it's repeated here in fancy typesetting. So going from station 1 to station 2, where station 1 is upstream of station 2, so flow is from 1 to 2. We have the energy, the specific energy at the upstream section, plus the channel slope times the spacing, which essentially that's gravitational drive term, is equal to the specific energy at section 2, plus the friction slope, so that's a head loss term. So energy at 1 plus gravitational driving forces equals energy at 2 plus head loss. And we can rearrange that a bit as follows. We can rearrange it that the bottom slope minus the friction slope is equal to the difference in specific energy between the two sections, E2 minus E sub 1, divided by the spacing, delta x. And if we take the limit as delta x approaches 0, we have the result that the difference in bottom slope and friction slope is equal to the first derivative of the specific energy function with respect to x, or dE dx, or the slope of the specific energy line. And that allows us to do a little bit of algebraic manipulation with our other terms we've previously defined. So let's go ahead and do that. So we have S0 minus S sub F equals dE dx. We've just established that in the previous slide of the presentation. We can use the chain gang rule and re-express dE dx as dE dy times dy dx. Turns out dy dx is something that we've seen but we've not defined yet. And I will defer that for a few seconds, but it's actually appeared in the pictures already. Hence, we can now examine the change in specific energy with change in flow depth. It turns out that that's 1 minus q squared over ga cubed dA dy. And it turns out that this term here is something called a Froude number. It's a dimensionless number. So the change in specific energy with change in flow depth is 1 minus the Froude number squared. dA dy we saw in the last class lesson. That was the shaded sliver of water in a channel. As we move the y value up and down, we actually integrated dA dy to obtain the cross-sectional flow area. Q squared over Ga cubed is essentially this expression right here, integrated with respect, differentiated with respect to the variable y, the flow depth. So let's go ahead and make that substitution. So we have S0 minus S sub F is equal to 1 minus the Froude number squared times dy dx. And we'll rearrange that one more time, and we have dy dx is equal to S0 minus S sub F over 1 minus the Froude number squared. And let's examine these terms. So dy dx is the variation of the water surface elevation. It is the slope of the hydraulic grade line. The friction slope term is dependent on discharge and cross-sectional geometry. So it will change depending on different values of flow, and it will change depending on whether we have triangles or squares or circles. The Froude number likewise will change based on the values of flow, and it will change on whether we have squares or circles or triangles. S0 is essentially a constant between each section because it's defined as the slope of the bottom surface, and 1 is the integer that appears between 0 and 2. I'm being a smart aleck there. And so that produces what is the basic equation of gradually varied flow. And what it does is it relates the slope of the hydraulic grade line to the slope of the energy grade line and the slope of the bottom grade line. And if we could integrate this equation, we can use it to find the shape of the water surface and hence how full a sewer will become. And that's why it's important. So before getting into these water surface profile calculations, we have to define something called critical depth and supercritical and subcritical. And these are defined based on various flow regimes. So if we take the specific energy at some cross-section, we can write it as E, the energy function, is equal to Y, the flow depth, plus Q squared divided by 2GA squared. And I'll let you figure out that that's just V squared over 2G. And it turns out that the specific energy is a function of depth, Y. It's a function of discharge, Q. And it's clearly a function of geometry, A. And at some section, if we were to plot depth on the horizontal axis and energy on the vertical axis, as we change the depth for a fixed value of Q. So for some set value of Q, say 10 cubic feet per second, if we started to adjust Y, we would find a function that might look something like drawn here. At one point, it would have a minimum, the minimum energy, and that is called the critical depth. It's the depth for a fixed value of flow rate in a particular channel at which we have minimum specific energy. The more common way of plotting this diagram is shown here on the right, where energy is plotted on the horizontal axis and depth is on the vertical axis. And there is a, if you will, a smallest value of energy on the plot, which is the critical energy, critical depth. This way of plotting is probably more common because our brains easily associate the up-down axis with depth. This also has the convenient way of telling us the fraction of energy that's associated with depth and the fraction of energy that's associated with velocity. So with that in mind, let's examine this critical flow concept. So I've just asserted that there's a minimum at Y sub C. If that's true, then the change in energy with respect to depth at that critical point would be 0. That's a necessary and sufficient condition for a minimum to exist. And you had that in calculus, that just means the gradient has to vanish. So let's go ahead and express the dE dy is equal to 1 minus Q squared over GA cubed times dA dy. So that's the variation of energy with respect to depth, in this case written in discharge form. Let's look at the dA dy term. It turns out that dA is this small little sliver of area. As we add just one more dy unit of water to the channel, and then T is the top width at that point. And so the top width times dy equals dA, and so the dA as a function is equal to T dy. Keep in mind that the T, the top width, is also a function of Y. Making that substitution, we have dE dy equals 1 minus Q squared times the top width divided by GA cubed. And this is the variation of energy with respect to depth in discharge form, incorporating the top width. So at critical depth, that gradient has to equal 0, which means the left-hand side of the equation, dE dy equals 0. So we have 0 equals 1 minus q squared t over ga cubed, or q squared t over ga cubed has to equal 1 for us to be at the critical depth. It turns out that this group of hydraulic variables on the rightmost side of that equation is a Froude number squared. So it's a dimensionless number. If you've never heard the term before, it's like a, well, you've had Reynolds numbers in your fluids class, so you've seen dimensionless numbers. Froude number is a different version of that. And critical flow occurs when the Froude number is equal to unity. And the Froude number is the ratio of inertial forces to gravitational forces. So the upper part of the Froude number is the force involved with the fact that water is moving, and the lower part of it is the force involved with the water being pulled downhill. Knowing this, the ratio of inertial to gravitational forces isn't necessarily useful, except maybe conceptually. All right, so now we've defined what critical depth is. We have the top width and area are themselves functions of y. And we can leverage that shortly. But let's now define what's meant by supercritical and subcritical flow. So here I'm returning back to the original way of plotting it, where energy is on the specific energies on the up-down axis, and flow depth is on the horizontal axis. And this curve that the cursor is following is the specific energy versus depth curve for some prescribed value of discharge Q. And what we have on the energy axis is, let's pick this point that's labeled critical. As we move up on the energy axis, this line here, the diagonal line, is a one-to-one line, and it corresponds to the amount of energy at the section that's attributed to flow depth. So right here we have this amount of energy that's attributed to how deep the water is. And then the remaining energy is kinetic energy. So getting up to the curve is the kinetic energy. So everything above that diagonal line represents velocity head. Everything below the diagonal line represents pressure head. If we move off the critical depth is the case where we have the minimum total energy. As drawn here, it's almost like the flow depth is about the same as velocity head. That's coincidental with the hand drawing. As we move to the left, we have less energy associated with flow depth and a greater portion of energy associated with velocity, and that's called supercritical flow. It plays the same role in liquids that supersonic flow does in gases. Supercritical flow tends to have a lot of velocity head and not very much pressure head. And it's called supercritical because the value of Froude number is going to be larger than 1. If we move to the right side of the critical depth, we have more flow depth and less velocity, more energy explained by the depth of flow than by velocity. And these tend to approach this one-to-one line. And in that case, we're in what's called the subcritical regime. So a lot of our energy is attributed to how deep the water is. And there's a little energy associated with how fast it's flowing. But most of the specific energy is associated with depth. Those are called subcritical flows. And they actually get their name because the value of the Froude number is less than 1. What's interesting to me is, like, on the subcritical regime, Froude numbers range from less than 1 to something bigger than 0. But on the supercritical side, Froude numbers go from greater than 1 to a lot greater than 1. They can have values of like 2 as high as 20 or 30. So the range that Froude numbers take on the supercritical, subcritical side is quite different. On subcritical, they're constrained between 0 and 1. Supercritical, greater than 1 up to as big as you can get until the liquid actually tears itself apart molecularly. So the flow regime itself affects the slope of the energy gradient. So we can see the slope on the supercritical side as we approach critical depth is actually quite steep and negative. And then once we pass critical depth, the slope of the energy grade line is not so steep and it has positive values. We use that in practice to figure out which way we have to integrate the gradually varied flow equation to recover a water surface profile. First, let's go find NEMO, or critical depths, in a rectangular channel. So we'll go back to our friend the rectangle, which is always a good starting point because it's easy to wrap our brains around it. So it has a bottom width of capital B and a flow depth of y. We know the depth area function is simply b times y, and the depth top width function is the constant b. If we were to make the various substitutions into the critical depth equation, we will substitute t of y into this location in the Froude number, and by into that location in the Froude number. Perform the indicated arithmetic. So 1 is equal to q squared b divided by g times b cubed y cubed, which equals q squared divided by g b squared y cubed. And if we were to solve this expression for y, we would be solving it for the critical depth. So in a rectangular channel, the critical depth is the cube root of q squared over g b squared. When the channel is not rectangular, obviously this expression is going to be more complicated, and we may not get as clean we may not get a closed form solution like we have for rectangular channels. It looks like I'm trying to do that for trapezoidal channels. So going with the same analysis again, we have the depth area function for a trapezoidal channel. We have the depth top width function. We substitute the expressions into the Froude number squared equals 1 requirement. And when we get done, the best we can get is q squared times the quantity b plus 2y over m divided by g times the quantity by plus y squared over m to the third power, and trying to perform algebra to recover y out of that. I'm sure it's possible, but that's quite a bit of unnecessary work. What I would do is go ahead and code this up as a function in a spreadsheet or a script, and then guess values of y until the Froude number squared equals 1, or if I subtract the 1 off of this, I guess values of y to make the function equal to 0. And if I chose that second approach, I could use Newton's method to find those values. It would find them pretty quick. I would say trial and error is adequate, and we could proceed. We also could use HEC22 design charts, because that's what they're for. But let's go ahead and just do one trial error example. Let's suppose we have a trapezoidal channel that carries 5,000 cubic feet per second. The channel bottom width is 20 feet, and it has 1-to-1 side slopes, so that would be 45-degree sidewalls. That'd be a pretty steep side channel, but they exist in practice. And we want to find the critical depth. So to do that, we set 1 equal to q squared t. over GA cubed. And then we insert the algebraic representations of top width and area as a function of depth. And then we're going to guess, we will substitute numbers everywhere we can. And so we have this equation, 500 squared over 32.2 times 20 plus 2y divided by 20y plus y squared quantity cubed is equal to the Froude number squared of y. And what we're going to do is we're going to guess values of y. We're going to compute values of Froude number squared. And we want to get the value of y that makes it close to 1. So if we guess our first flow of 1 unit deep, we get a Froude number squared of 18. That is supercritical flow, and that's way too big for our goal, which is the critical depth. So we increase it to 2. Froude number has dropped to 2.2. We're still too big, but we're headed in the right direction. We go to 3. We would compute a Froude number squared of 0.6. We're now too small, and we've moved into subcritical regime. So split the difference, 2.5, get a Froude number 1.09. We're pretty close. 2.56, 1.01, and that's probably the best we're going to do doing it with a hand calculator. There'd be no benefit, in my opinion, to going any further. So roughly 2.5 feet is 2 feet 6 inches, and a tenth of a foot's about an inch, so 6/100ths of a foot's a half an inch. So we're at 2 feet 6.5 inches flow depth is critical depth in this channel. One thing I'll call your attention to is you notice the bottom slope doesn't appear anywhere in these critical depth calculations. Critical depth is a property of the channel geometry only and not the slope of the channel. We also can go finding critical depth in circles, again using the same formulas as before. So we have these circular formulas from our last class meeting, and we can substitute them into the Froude number calculator. In this case, Froude number squared is q squared d sine alpha g d squared over 4 alpha minus sine alpha cosine alpha. And so what we'll have to do is we guess a value of y, we compute alpha, and then we can compute a Froude number. Oh, thankfully I don't do an example of that. That would just be a lot of calculating. But you could code that up, and it's really not that difficult in that context. So that's our background. We now know what critical depth is. We've seen the gradually varied flow equation. We know what specific energy for a cross-section is. So let's use that to find a water surface profile. So what we want to do is integrate that equation, and the integral looks like this. So this is just notation. Only a fool would attempt to actually do the integral. But the hydraulic grade line as a function of x, which is location in the channel, is equal to the integral from some starting x0 to some x1, some point of interest, of dy dx, which is dy dx is the slope of the hydraulic grade line, and we would have to add to that the integral of dz dx. dz dx is the slope of the bottom of the channel. So essentially we compute what the flow depth is, and then we add the channel bottom to that, and that gives us the water surface elevation. And the variable of integration is dx. So if we substitute the different terms, that's the integral from some starting point x0 to some point of interest x1 of f0 minus s of f over 1 minus the Froude number squared plus dz dx, all with respect to x. So what this equation is trying to tell us is we find the water surface profile by integrating the depth taper, the distance, and then adding on the bottom. But wait, there's more. First, we have to describe what's meant by channel slopes and profiles, because these affect the integration. The integrations, by the way, they're all done numerically. There's only a few shapes that are amenable to analytical solutions. There's no advantage. So they're almost all done numerically. But we have to know what's meant by a steep channel, a critical channel, a mild channel, kind of sounds like we're talking about salsa, a horizontal channel, and adverse. So a steep channel, by definition, is a channel where the normal depth, which was the subject of Tuesday's lesson, and the critical depth are such that the normal depth is smaller than the critical depth. If that's true, then that's the definition of a steep channel. If the normal depth and the critical depth are equal, that's the definition of a critical channel. And if the normal depth is greater than the critical depth, that's the definition of a mild channel. And all three of these occur in practice. Critical channels are, to some extent, somewhat rare because critical flow is difficult to maintain over long distances, certainly in natural systems. Engineered systems can be made to do that. So the Salt River Aqueduct that takes water from the Colorado River to, I think it takes Tucson, Arizona. I may have my geography wrong. Those are engineered to run really pretty close to critical depth. There's a few others of that genre. These are all pretty common. A horizontal channel is exactly what it sounds like. If the bottom slope is 0, that's a horizontal channel. An adverse channel is the case where the water is flowing uphill relative to the channel bottom. And that happens quite often over relatively short distances. And in fact, we leverage that in dam spillways as a way to burn up excess hydraulic energy. We actually let the water run down the spillway. It gets a good head of steam going up, and then we force it into a channel where the channel bottom rises as the water moves forward, and so it's having to flow uphill, and the flowing uphill uses up a lot of energy. With regards to the channel slopes, there's also 3 profiles in gradually varied flow, type 1, type 2, and type 3, because we have no originality in hydraulic engineering. So let's look at what each type is. If we have the case where the computed depth is greater than critical depth, and the computed depth is greater than normal depth, then that's a type 1 channel profile. If the critical depth is less than computed depth is less than normal depth, or normal depth is less than computed depth, this should be a C. Less than critical depth, that's type 2. And if the computed depth is less than critical and the computed depth is less than normal, we have a type 3 profile. And the type 1, type 2, and type 3 in combination with the slope designation helps us determine which way to perform the integration. So let's just look at a few of them. Let's look at an M1 profile. M means mild, and 1 means it's a profile type 1. These are characteristic of cases where there's some sort of downstream control affecting the water flow, and the water surface is called a backwater curve. And examples of this is flow coming into a pool, say just upstream of a weir or a dam. And if we wanted to compute the water surface profile, we start at a known location and we're going to work upstream. So M1 profile, we would integrate moving upstream. In M2 profile, we have still a case of downstream control. Something downstream is affecting behavior. But the computed curve is still called a backwater curve, And an example of where this occurs is the flow is accelerating to go over a break and slope or maybe go over a dam. And as before, we'd go from a node point and we would integrate moving upstream. And then an M3 profile, as an example, is a case of upstream control. The backwater curve in some context is called a front water curve. Name's irrelevant. Example is flow coming out of a sluice gate and it's starting to decelerate and get more and more flow depth. And in the case of the type 3, we want to integrate from a known point working downstream. And we have the same kind of relationships for steep channels. So in a steep channel, the shape of the curve is different. Instead of being concave upward, it's concave downward. But we're still under downstream control, and we would integrate moving upstream. S2 profile, we have a supercritical case, and S3 is also supercritical, headed towards normal depth. We'd integrate downstream. There are many other examples. So any hydraulics textbook, such as the one on the server, we'll go take a look at that, usually has tables of flow profiles. And the flow profiles help us identify control points to start the integration, as well as the direction to integrate. If we're using commercial software, we won't necessarily have to pick the direction to integrate, but we still have to identify control points, and we have to instruct the software which way we want it to produce water surfaces. So I want to take a look at this, and I'm pretty sure this will have pictures of profiles. If I'm wrong, I will know it in a minute. Should be playing the Jeopardy theme now. We pretty much, that picture should look familiar. Critical flow, critical depth. Oh, it might be wrong. Write that down in your calendar. I was wrong. There we go. I knew it would have pictures of profiles. So my hand-drawn ones are pretty much conveying the same thing that this set of images is conveying. So critical under mild, steep, horizontal conditions. So the zone 1, zone 2, and zone 3 were what I would call type 1, type 2, type 3. And these are used to help determine water surface profiles. So this line here that the cursor is following in this particular picture, that is often what we are after in our engineering design, because we want to be sure that the location of that is what we want it to be to satisfy our drainage engineering needs. And the next thing this goes into is how to do those calculations. We'll take a look at those ourselves, although between 1980 and the present, there's a lot more software available to do the work for us. So one of the ways to do it if we don't have software is something called the variable step method. And in this case, what we're going to do is we're going to choose a set of flow depths, and we're going to determine the space in between those. It works for prismatic channels only, and that's a geometry requirement, and it's going to produce non-uniform space steps. So it's not necessarily that useful for engineering design, although it can be forced to work if nothing else will. And so how this works is, consider two sections, section 1 and section 2. We write the specific energy equation for the two sections, and we rearrange it and we make the unknown equal to the space between the two. And presumably we know what bottom slope is, and we can calculate friction slope. So as an algorithm, we would start from a section with a known depth. So step one is vital. If we don't know the flow depth at some point, we can't proceed. Then we would calculate the specific energy for the starting section, where we have the known depth. We would calculate the friction slope at that location. We calculate the friction slope by Manning's equation, just rearrange it for slope and solve it for the required slope that makes the rest of the equation true. And then we adjust the depth slightly, that's our y2 value, and calculate the specific energy at section 2. We don't know where section 2 is yet, but we have asserted its flow depth. We calculate the friction slope at the new section. We compute an average friction slope. The average friction slope is going to go right here. And then the known bottom slope goes right there. The computed starting energy and the computed energy at section 2 go in their respective locations. And we're going to solve for delta x, the space between the two sections. Once we've done that, we write it down, and then we move on to the next section and repeat. So let's just go through a simple example numerically. Let's suppose we have a rectangular channel, 1 meter wide. It's carrying 2.5 cubic meters per second. It has a bottom slope of 1 part in 1,000. That's actually a pretty shallow channel. It has Manning's end of 0.025, which is somewhere between what we would expect for a concrete and grass line channel. So this is perhaps an improved channel with all sorts of shopping carts and car parts in it, a few refrigerators, a dead cow or two. And the water is flowing over a weir at some location at exactly 2 meters deep, just upstream of the weirs. So here's the drawing. We have a control point. We'll declare this x equals 0, and we know the flow depth there is 2 meters. And we've been tasked with what's the water surface profile. So we would create an energy depth function. In this case, because it's a prismatic channel, certain constants, we can incorporate them directly. And so we have the 2.5 meters cubed per second from the flow. We know it's a 1 meter wide channel. We know it's rectangular. So we can substitute the numerical values in here and come up with the specific energy equation for this channel under those flow conditions is 0.32 divided by y squared plus y. The friction slope for that channel under these flow conditions is given by Manning's equation. Here Manning's equation has been rearranged to solve for the friction slope. So the area has to be known, hydraulic radius is known, Q is known, Manning's N is known. We substitute the value for discharge, we substitute the area function, we substitute the hydraulic radius function, which for a rectangular channel is pretty easy to do. And we now have an equation in terms of depth that returns friction slope. And it looks like I didn't bother to substitute in Manning's N, but we would substitute that value in. And now we can begin. So we started our known sections. So section 1, flow depth is 2. Specific energy is 2.079. Friction slope 0.000114. Bottom slope 0.001. And we're at station 0, and there's no delta x that we've come from. And now we'll compute the first upstream step. So the next flow depth we're going to use is 1.8. So we use 1.8 flow depth, which gives us a new specific energy, our current specific energy at section 1. So this is specific energy at section 2, S0. minus the average friction slope produces minus 0.181 divided by 0.000865 for a spacing of minus 209.3 meters. So we write that down in the second line of the chart. So the way this chart was actually built is we did the whole first line, and then in the second line we wrote the 1.8, we computed the 1.898, computed the 0.00157, the 0.001, and then we made this calculation right up here. We wrote that in, and our new station is minus 209. The minus means we're moving upstream. Then we go ahead and write our third line. Let's go down to 1.6 meters of flow depth. Specific energy is 1.7. Friction slope, 0.000225. Bottom slope. And then we compute the change in spacing between section 2 and section 3, which turns out to be minus 215 meters. So we have that minus 215.1 meters, to which we add to the prior station. So we now have minus 424.3 meters. So our flow depths in this channel at station 0 are 2 meters. 209 meters upstream of station 0, it's 1.8 meters deep. 424 meters upstream of station 0, it's 1.6 meters deep. And we can repeat that as far as we want to. And then we would use that to plot what the system looks like. So we have these flow depths at the different stations, and then if we added on the known bottom elevation, we can draw the water surface elevation. And that's called the variable step method. The fixed step method rearranges the energy equation somewhat differently, in that we have the energy 2 is equal to the energy 1 plus S0 minus S sub F divided by the spacing. This is far more useful for engineering, but it's an implicit nonlinear equation. And so we want to use software to do that for us, such as SWIM or HEC-RAS, or we can take the open channel flow class, and they should go through the computational aspects of the fixed step method. And then the whole point of that, again, is to find water surface profiles. So this slide is going to suggest how to do it for circles. And we could do the water surface in a circular pipe on a 0.001 slope using Manning's N. Supposing we have a downstream control depth of 8 meters. And at this point, it's complicated enough that we want to use a spreadsheet. So we would start with our known section and then compute delta X and eventually plot it. So let's see what a 10 meter diameter pipe, that's 35 feet across. You can drive a truck through that. And 8 meters deep, that's 24 feet of water. So this is big. But we can plot the bottom elevation, in this case in orange, and the flow depth is added to the bottom elevation to give us a water surface elevation. This is pretty flat for these particular conditions. So let's go look at some of those spreadsheets. How are we good on time? And we'll first look at I hope this is the right one. I'm going to use the 2018 one because I have a feeling that's probably the one I want to use. Cool. So here is a area. This is not the same one from the lecture notes. But here we have 55 0.4 cubic meters per second in a channel that has an N value of 0.02. And let's just look at, I want to call your attention up here to the, oh, it didn't get any bigger there, does it? No. That was worth a try. Keep your mind up here, keep your eye up on the formula thing. So the first depth is a known depth, so we're supplying that information. Known width, area, look at the formula, it's width times depth, so this is clearly a rectangular channel, although it says it is. We calculate a hydraulic wetted perimeter, which is twice the depth plus the width. Hydraulic radius, which is area divided by wetted perimeter. And then we compute a velocity, which is to take the discharge, the 55.4, and divide by the area at this section, which is 40, for velocity 1.39. We calculate specific energy as flow depth plus velocity squared divided by 2 times 9.8. We calculate friction slope as Manning's equation in reverse. Bottom slope is an input, and we're at station 0. There is no spacing change. Bottom elevation is 0. Our water elevation is 8 feet. And when we move to the second line, so we're now going to try to find the distance to where the flow depth is 7.8 feet. Width doesn't change. Area is recomputed for the new flow depth. Wetted perimeter for the new flow depth. Hydraulic radius for the new flow depth. Velocity for the new flow depth. Specific energy for the new flow depth. Friction slope, Manning's equation for the new flow depth. Bottom slope's an input. And now we're going to compute the required delta x. And so if we look at the formula, it's taking the specific energy at the current section minus the specific energy of the upstream section divided by the average slope divided by the average friction slope to compute a spacing change. So it says we have to move 293 meters upstream to get to a flow depth of 7.8 meters. In this case, the stationing is minus 293. The bottom elevation for that location is 0.293 meters. We add the flow depth of 7.8 and the bottom elevation for a water surface elevation of 8.09 meters. And then we simply repeat that process for different values of depth. And when we get done, going all the way down to 5, and we don't want to go much before 5, what will happen is if we go too shallow, basically we pass through normal depth for the section, the sign of the delta x will change. And that's just an indication that you have you've passed through the normal or the critical depth for the section. Now when we plot it, this may be able to let me do what I want. And so now we've plotted all these on a chart. Here we have the bottom elevation plotted in brown, and the water surface or the hydraulic grade line plotted in blue. And how we would use this next is if we had a structure at minus 6,000 feet next to the channel whose finished floor elevation was at, these are meters, at 10 meters, that would be problematic because the hydraulic grade line is above the bottom of the structure. And so we want to make some design changes. Alternatively, if this happens to be a sewer pipe and the hydraulic grade line goes above the top of the pipe, in that location, the sewer is going to have to operate surcharge and there'll be a potential for water to escape from the system. Let's save that. And it looks like we have a similar calculation for a circular one. Let's go ahead and take a look at that. Yeah, this one is from the notes. Admittedly, it's a somewhat contrived problem because 10-foot diameter, 10-meter diameter sewers is pretty unusual. So it's conveying 11 cubic meters per second, Manning's N of 0.02. Same approach as before. We have a depth. We now have a diameter. Once we have the depth and diameter, we can compute alpha, that angle. Then we can apply the area function, the weighted perimeter function, compute a hydraulic radius, compute a mean section velocity, specific energy for the section, friction slope, bottom slope, and the location of the water surface elevation. Then we move to the next section. We don't know where the section is yet, but the diameter is constant. We calculate the new alpha, new area, new weighted perimeter, new hydraulic radius, new velocity, new specific energy, new friction slope, and calculate the spacing change. So it's minus 200.4, and that gives us a station of minus 200.4, so we're moving upstream. We know what the bottom elevation is there. It's conveniently, it seems to be 0.2, and we add the depth to the bottom elevation, and we see the water surface elevation is still pretty close to 8 meters. And we repeat that as we're moving upstream in the system. Make sure there's no sign change. And there is the plot of our water surface elevation in this circular pipe. So what's happening over here on the left-hand side of the graphic is we're pretty close to normal flow depth here. And then as we reach the 8-foot pond, the water's starting to pile up and form a pool. So the flow at the left end and the right end is the same. This is a classic backwater representation. And but far enough upstream of the pool, we have normal flow. So well, that's all fun and games to do. That's not terribly useful for design, other than to give you a rough idea what's going on under the hood inside a computer program. Here's similar things that are done in a different environment. This is the R scripting language. And I'm going to go ahead and try to get a local copy running. So I think I want RStudio. I may want it, but it looks like I'm not going to get it. Fine. Let's do it in native R. No, I don't want that. I want RStudio. I'd really like this thing to work. There we go. So this is, I think, the same as the example problem done in the spreadsheet. And so it's produced a flow depth calculator for different distances. And let's see what the example it did. Beginning depth. Let's change that to this guy. See what happens. So this is a example where we're starting at a depth of 4 meters, going to 3 meters. Yeah, it's in SI units, and we're plotting 31 points. Discharge is 5,000 units, and the width of the channel is 1,000. So that's a kilometer. This is a very wide channel. Manning's end is 0.022. Slope is 0.048. This is an example from an old hydraulics textbook. Quit doing that. So that is an example in a different scripting language, actually written as a function. Let's see what backwater curve. So this is a trapezoidal channel. So we'll take a look at that, and hopefully I have an example. Looks like it's also set for US customary. It does nothing. So this is in a trapezoidal channel, and let's see what method it's using. Yeah, this is using the same method as before, so the variable step method. And we'll take one more, because I think I have one that's done in the fixed step method. US customary fixed space water surface profile. So this is the fixed space method for a backwater curve, and we'll just look at it if it's actually going to work, or is it going to I don't want to do anything mode. So notice all my file names, there's a bunch of junkers here. So I'll get rid of more junk and junk. So let's see what we have. We have Manning's end of 0.033. We have a channel slope of 1 part in 1,000. The upstream station normal depth is given as 5.6 times 3.28. The control depth is 9.7. These look like these are conversions from meters to feet. And the spacing between stations is 3,200 feet. So this is the first one that we're actually going to be able to specify the required spacing. So this is much more like how we would want to do it for design. And our design choices might be whatever the widths are at different space. And let's go ahead and run it. Hopefully it's still working. Okay, cool, it is. And so here's our water surface profile. And we see there's this hump here, and there's depression, and then this jump here. And let me see if I can find the picture that goes along with it. I cannot. The plan view of this particular channel looks like it has a narrow section. And the narrow section is where the water is accelerating to get to the pool. So in plan view, this is not a rectangular channel anymore. It's a channel that is 10 units wide, going up to 11, 12, 13, 14, 13, 12, 11, 10, 9, 8, 7, 8, 9, 10, 10, and 10, and 10. So it has a narrowing and a widening and then a narrowing. And we can use that to mess with what the water surface elevation is in particular areas. So actually, the fixed space method is really not all that complicated. It is in the next 10 seconds, because it's just some looping through, and essentially it's doing root finding at each cross section. So when you take your numerical methods class, this is a classic method attributed to Hamming, who was a one-time famous numerical method dude. So let me quit that. Don't save. So you can visit those on your own, and you have the spreadsheets to look at. But what we'll do in the class is mostly stick with the SWIM computer program, which essentially does a version of Hamming's method. Not directly, but close enough. And so now you've seen the underlying theory that goes on in the computational processes of open channel flow. Are there any questions? We got a few minutes for questions before we terminate the call and go on about our day.
I have a question on the homework.
Yes?
For the storage tank on part 1, or the reservoir on part 1, what's the elevation for that?
Oh, you have to pick it. That's how you can. That's how you can control what the pressure is at node 1.
Okay, so we can decide for that part.
You're going to have to, otherwise you won't be able to get an answer.
Okay.
I'm not playing trickery on you, but that would be how you would resolve that question. That's a good question. So you'll put a reservoir in to connect to it. You choose the reservoir pool elevation so that the node 1, I think the problem statement says the head at node 1 is 100 feet. I seem to remember that. Let's see if I have a copy of the exercise here on the evasive server. That's the EPANet application. Your table 1 is a list of everything. Yeah, determine the flow rate in each pipeline network for the case where the total head at node 1 is 100 feet. So you have a reservoir out here attached to this red arrow, correct?
Yes.
You're going to mess with the elevation in that reservoir so that the computed head at node 1 is 100 feet. And that's how you will solve that. That's what's requested by this problem.
Okay, thank you.
And it brings up a very good point. Is this the second part of the question? Is we're told that the water main right here supplies water at 135 psi. So from a hydraulic modeling perspective, we can replace the water main with a reservoir whose pool elevation produces a pressure of 135 at that location. And that's what we want to do to evaluate if we have to introduce boost pumps in this system or not. So the question and the resolution are related to each other in these two problems. Good question, thank you. Has everybody so the other question is, how do you select the pipe from the reservoir to node 1? pretty much any way you want to. I would, for me, because I don't really care what that pipe's doing, I'd probably make it a very big diameter pipe so there's no head loss in it, because it'll make it a whole lot easier to adjust the reservoir elevations. If there's no head loss in it, the reservoir elevation is the head at node 1. So that's how I would do it. And I suppose you could do like an 8-inch pipe and see what happens, but there'd be more trial and error in doing that. It'd still work. Any other questions?
Yes, I had a question about saving our work on EPANet. Every time I try to do so on the online server, I never seem to be able to find it afterwards. Is that just not possible, or do we have to kind of do it straight through the assignment?
That's a good question. Let me see if I can. Let me see if I can.
Or if there was a way to download EPANet onto our PCs.
Oh, of course there is. You can just go to the EPA website and download it and install it.
Okay.
You don't have to use my stuff. But let me go ahead and see if I can find your files. If you've already done it, they should be there. There we go. So I go to that guy. So does that look like the problem you were working on?
No, I did mine a little while ago.
Well, let's go. So it's supposed to point back to EPANet files, but so none of those are yours?
No.
Okay. Then let's go where, let's see, where's the EPANet save stuff ordinarily? Does AMCE?
Oh yes, that one's mine.
Okay, so let's go ahead and load it in. Well, actually, wait a second. It says the file no longer exists.
Cool.
Interesting.
I basically finished that portion of the assignment, so it's not too big of a deal, but I was just wondering in regards to the second one.
It's there somewhere, but let's see if I can remember where to find it. It'll be there. Not there. Okay, so it's going to make it hard for me, isn't it?
Yeah, I had difficulty finding it as well.
I just need to find the path. I know where it is. So home hydro 1. It's going to be somewhere in here.
Okay.
So let me get. I'm just going to take that much of it. Hopefully that's all I need. Give me the browser, damn it. Oh, my bad. Clicked on the wrong thing. Okay, home hydro 1. Line. FC. x86. So you usually store stuff like that somewhere in here, but I can't find it.
Okay, it's no worries. I basically finished that portion. I was just wondering. I'll probably end up just downloading it onto my PC so I can do the second portion.
Yeah, that you actually want to do that with Swim also. This is provided. I mean, you're all free to use this online thing, but you got to really think about your file management carefully, because if you just willy-nilly don't, you have experience losing it. I'm thinking it might be somewhere on the machine, but I can't remember how. I think it's. Do you remember the file name? It was.
It was AMC ES5. Yes.
Let's see if we can find it this side. AMCES cap C. Yeah, it's most likely quite gone.
It's no worries. Thank you, though.
Yeah. There's some other search tools, but I'd have to read how to use them. Because we're not supposed to be running EPANet on a Linux server. Apparently it's impossible, but it seems to be doing it right now. So that you bring up actually a good point. I didn't want that to happen. Let's see if I can relaunch it. So let's say we have that, and so we got this program here. We run it. Okay, we're happy, and I want to save that file. So we go File, and we have the Save As. And at this point, we have to do some thinking on where we want to put it. So I have it programmed usually to go to desktop EPANet files. But let's say we didn't know that. We went to this desktop, and I go, that doesn't look right. So we have to work our way back through the desktop. The one we want to go is we want to go to Home, and this is Hydro 1, and that desktop. And now we can get to our EPANet files. We save it right there, and that file's saved. I'll close it. If we go to EPANet files, there's the file right there. And you all are free, if you're going to use this, and encouraged to go ahead and make your own directories. And then all I'll do is ask everybody to be honorable and give them a directory name that identifies it to you, and then everybody else stay out of that person's directory. So my directory, there's Nico, files, and that's how to use this. But by far, if you have a PC, downloading it and installing it is just fine. If you have a Macintosh, your host, this may be the best way to do it. So thanks, Adriana. Any other questions? Okay, Marche, what we do is we go to EPANET, hit the return button, EPANet, downloads, there's the website. Alternatively, if you really don't want to do that, you can go to my server and get some legacy installers. And I think this one actually goes to the goes directly to the EPA one, and so forth. For Macintosh users, this is really important. As of July 2020, the last known working operating system was Mojave. So if you have something else like Catalina or Big Sur, won't work. But if you have Mojave, if you're still running Mojave, this EPANet Online will work. Cool. Actually, that's not bad questioning. And I think there's an exam that's due 11:59 tonight. I hope you all have either done it or started. I haven't looked to see if anyone's made progress on it. And I will go ahead and end the phone call because I just noticed that we're out of time. So thank you very much for your attention and questions and sticking through this stuff. And we're doing online, which would be a whole lot easier if we could do this in class face-to-face. The examples would be a lot better. They'd be the same examples, but they'd make more sense. Everybody have a great weekend, and I will see you on Tuesday. Stay safe, and all that good stuff that we're supposed to say. So have a great weekend. Bye-bye.